listening to Hear This Idea, a podcast showcasing new thinking from top academics at the University of Cambridge and beyond. Jaime Sevilla Molina is a researcher and PhD student focusing on questions relating to predicting the effects of emerging technologies. He's worked on topics ranging from the application of artificial intelligence in climate change to Bayesian reasoning and decision theory. We covered loads of ground in this episode: cultural persistence, the principles of good forecasting, the significance of quantum computing, and much more. So here's Jaime Sevilla.
So I'm Jaime Sevilla. I am right now a PhD student at Aberdeen under a Marie Curie grant studying Bayesian reasoning. My background is in both mathematics and computer science, and over the last year, I've been researching from the Future of Humanity Institute in Oxford in summer, and then over the course of the year, I've been in the Center for the Study of Existential Risks.
Now, when we were emailing about this interview, you said that the overall aim of your research is to, quote, predict the counterfactual economic and social impact of emerging technologies, cultural interventions, and policies in a decision-relevant way. I thought we should start by digging into that. So very simply, why care? What's so important about accurately predicting these counterfactual impacts?
Right. So I think that it's interesting to think about why are we interested in predicting the impact of these big sprawling things like new technologies, new policies, etc. There are two aspects to it, right? There's one that has to do with prioritization. We want to be able to tell which are the problems which are more urgent to deal with, so we can focus resources on them first. The second one, however, has to do with planning and action. And here's where the counterfactual bit comes in, right? You want to be able to tell whether investing in this particular new technology is going to have net positive effects for the world, or whether it's going to have bad consequences for the world. And in a more nuanced way, when you have many possibilities of investment, you want to figure out what's the technology that's going to have the biggest possible impact overall, right? That's the motivation, right? That's why we care about counterfactual reasoning, just and base predicting. But how do we do that? The traditional way of inferring causation is exploiting human cognition, right? Humans have been equipped with this amazing cognitive technology to detect causation. We know that if we drop the pen, it's going to fall to the ground. We have a very clear cause and effect model in there, which is tacit in the way we interact with the world. And generally, in the social sciences, what has been done in order to establish causation is try to exploit that by generating a theory that comes from the researcher's intuitions, and then validating that theory, or rather trying to falsify that theory via studying a correlation in nature. But this is not the only way. And we are, in the last 50 years or so, we have been learning about how to infer cause and effect in principle, which is a really exciting new field of knowledge that I'm hoping to be able to contribute to during my PhD.
So just to get clear on that, everyone has a decent intuitive understanding of causation, right? It's often just obvious that one thing causes another when it does. That could be, a light switch causing the light to turn on, or it could be some big economic factor causing some other big economic difference. But in the past, the social sciences, broadly speaking, have been a bit all over the place with this. So there's been a bit of a grab bag of different tools for inferring causal relationships from correlations. But more recently, we've seen this shift to a more unified, formal, mathematical approach to modelling causation. Is that right? And if so, what does that look like in practice?
That is correct. And economists have been trying to understand this better for the last 50 years, and they have made of headway into this. The overall framework that we work with today in order to infer causation is what's known as the natural experiments framework, right? It's like the situations in which like assignment of like a variable of interest happens like not exactly in a random way, but in a way that is not correlated with the outcomes of interest, right? So, so like for example, one of my avenues of research has to do with like reviewing the literature on like historical persistence of like examples of like how through history certain events led to cultural change, right? And like there's like this paper by Nathan Noon in which they are studying like the effects of like slavery in Africa. And this on its own is like really hard to tell. Like, how do you figure out what are the effects of like slavery, right? Like, you see that higher slave trade intensity is like associated with like lower trust, for example. But that's just like a correlation. Like maybe there is like a common cause. Maybe there's like a thing that both caused like certain places to be like lower trust and also more affected by the slave trade. So how do we tell? Well, we try to find this natural experiment, and what Noon comes up with, which we can discuss of whether this is like an appropriate natural experiment. But what he proposes is that distance to the coast is like a variable which like sort of predicts how big your slave trade intensity is going to be, but it is not correlated with trust, as he finds in his research. So, like he says, like, look, distance to the coast is like a variable that's sort of like randomly assigned to different places, whether they were going to be like high slave intensity or low slave intensity. So we can use that as sort of like to control the effect of like a slavery, right? And to figure out like what is the actual causal downstream effect of a slave trade intensity.
So you mentioned that we need to look for these kind of natural experiments, or I guess more recently as well, what economics has been doing has been actually setting up these experiments itself, right, through randomized controlled trials and the like. But presumably, this is actually a very strong requirement that is needed, and presumably that also really limits researchers into what they can reliably, study and evaluate when it looks for these causal things.
It does. It does. Actually, I will say that the big revolution that we're coming into is having like a more nuanced understanding of like natural experiments, so that we can like tell in principle whether like a particular thing is like a natural experiment or not. And like for example, like in medicine right now, like either you do a randomized controlled trial or like you do not have a result, right? And that's like hugely limiting. The fact that you can go from that to a natural experiment, that's like a natural widening of the scope. And like in the economic context, they have been doing like this kind of like natural experiment reasoning for a while. But like in order to like improve on that, we need a more mathematical understanding of like what exactly does it mean for something to be a good natural experiment, so that we can identify more in a principled way rather than just rely on like researchers' intuition.
Would you mind explaining in just a bit more detail what a natural experiment is?
So what people mean by natural experiment is like a situation in the world in which like the so to introduce like some terminology, when you're doing like this kind of like causation studies, you have like a certain like exposure variable, like some like what in medicine you will call the treatment, which is like the thing whose effects you're interested in. And then you have like the outcome you're interested in, right? And you're trying to figure out like, well, is there like a causal effect from this exposure to this outcome? And like how big is that effect? Like how important is the exposure of like a slave trade intensity for the outcome of like trust? And what is in this context a natural experiment? Well, it's like a third variable, which is what we call an instrument, which like semi-randomly assigns the exposure. So like in this case, it will be distance to the coast. And what I mean by semi-randomly, well, there's like a technical meaning behind it that has to do with like this instrument has to predict the exposure. We need to be able to tell like how much exposure is there going to be depending on the level of depending on the value of the instrument, but it doesn't have to have a direct effect on the outcome. Like otherwise, it will be biasing the study. Like if we found out that like distance to the coast had like an effect on trust that is not mediated by slave trade intensity, then that will render our instrument like invalid, or like at least it will force us to need to find out like what are these other mediators so we can control for them.
Yeah, I was just trying to think of an example. So you might see that ice cream sales correlate with cases of sunburn and wonder whether eating ice cream causes sunburn. But here there would be no causal influence because presumably you would spot that there's a common cause, right? How sunny it is. Another way you can find out is to do a randomized control trial. And you could give free ice cream to half of your randomly chosen group and see if it makes a difference to how many people get sunburn. And obviously it won't make a difference. But you might find that exposure to the sun does cause sunburn. Firstly, because you can't think of a similar common cause, which totally screens off the relationship. And secondly, because you could manipulate sun exposure in a similar way. That's the difference, right?
And like this has been like what I will dub like the traditional approach, right? It's like instead of like finding like this experiment-like situation, you think really hard about what are the possible common causes, and you explicitly control for them. But this has like an obvious shortcoming, which is that you're limited by your creativity and your ability to measure things in the world, right? So we want to make do with like engineering situations in which like you do not have to find like all possible common causes that may be like confounding your result.
So just to try and think of maybe an easier example to try and help visualize that before we unpack Nunn's paper on the slave trade. So for example, let's say that I want to look at, for example, the correlation or the causal effect between people using a job website and their employment afterwards. If I just look at that, then it's very hard to try and establish causality because the people who tend to use job websites might just be inherently more motivated to find a job, and therefore their employment is going to be much higher. And I can't say that, okay, these people who use job websites, it's the job website that causes them to find a job. So instead, I need to look for this third variable that's related to the chance of you using a job website, but not employment. So, for example, I know like a classic thing that economists like to use is rainfall, because obviously rainfall has nothing to do with if you're going to be successful getting a job or not. Rainfall is pretty random. But if it rains very heavily, then I might be indoors more. And if I'm indoors more, I might use the computer more. And if I use the computer more, then that could also mean I'm just bored and use a job website. So that would be something that is correlated with what I'm interested in, which is the job website, but not the outcome, which is the job.
Exactly. That's like a wonderful example.
Cool. Let's talk about the Nunn paper then. So you framed this in terms of cultural persistence. Can you briefly explain what you mean by that and what exactly Nunn was looking when he was examining this paper?
Yeah, so like I think it might be helpful to situate this break in its context. So like this is part of a literature review that I am doing for Professor William McCaskill, where like we're interested in like studying historical examples of like certain events or interventions that had like a long-term effect on culture, right? And this is exactly what we mean by cultural persistence, right? So like in this example, we're interested in studying how slave trade affected like long-term cultural norms in Africa.
Do you mind just really briefly explaining what the Nunn paper did and what it found? Just because I think that kind of context might be useful for listeners as well.
Right. So I've been looking at like actually three papers by Nunn. The first one has to do with like studying the relationship between a slave trade and modern GDP per capita in African countries. The second one has to do with studying the effects of like a slave trade on trust. This is the one he co-authored with 1 second. And the third one, which is the one he co-authored with like Alessina and another author, is the one that has to do with studying the effects of agriculture, different kinds of agriculture, particularly plot agriculture on gender norms today.
And we talked about these kind of natural experiments things before as well. Can you just unpack as well what kind of natural experiment you used to be able to cleanly identify the causal effect, or at least try to?
So in the first one, the one about the economy, he uses the instrument of like distance to the coast. He also uses distance to the coast in the second one, more convincingly in my opinion. In the third one, he's using like land suitability. And like right now, I'm in the process of like trying to figure out whether like there might be some issues with these instruments, which is a fascinating process.
So, for example, and this is just kind of thinking what problems there might be, because you need to be really careful, right, about choosing instrumental variables. Being on the coast can also kind of have other effects, right? So, for example, you might be more connected to international trade or the like, and if that is somehow related as well to trust or economic GDP, then that can kind of confuse the relationship. You're actually measuring two things at the same time.
Yes, which is one of the things that I am actually confused about right now, which is that in the paper, he actually goes through the exercise of checking whether like distance to the coast is like correlated with trust. And he finds that only in Africa it is correlated with trust. And this is like very surprising to me because distance to the coast is like a very deep economic factor. Like cities sprawl next to the sea because trade is easy.
Yeah, so you gave this context of Africa, and obviously the slave trade is such a big event in terms of both scale and length of time, that we would really suspect that if there is cultural persistence, if that kind of phenomenon exists, then we would very much expect it to happen in Africa during the slave trade. So can you explain a bit more about the hypothesis kind of going in that Nunn had about how slave trade might have changed the culture in Africa itself?
Yes, so like the historical account that Nunn is proposing, supporting this hypothesis, is that during the slave trade, lots of people started kidnapping their neighbors and selling them to Westerners for guns. And like that caused like a cultural shift of like people starting to distrust each other more, and like through some mechanism mediated by parentage, which more likely is something along the lines of like education, like that distrust had like a measurable effect that persists to the modern day.
And why might we care about this? And so obviously, slavery and this whole kidnapping thing is really horrible in of itself. But is perhaps especially interesting why we might care about this from a long-term perspective. How might this mistrust that happened hundreds of years ago still affect us today?
Yes, exactly. So we're interested in this not only in terms of like how it is affecting the present world. Like we're studying this example. We're also studying other examples like the effects of historical agriculture on gender norms and effects of the Western church on Western psychology. This kind of like examples are sort of like helping us form an intuition about like how tractable it is to change culture in the long term, because arguably like promoting like certain values that we are like very sure that are associated with like positive outcomes, like things like consequentialism, things like broadening your circle of concern. Like if we could affect persistent change on like these kind of values, that could potentially be like the most important thing that we could be doing nowadays, like trying to make sure that those values get like disseminated and like have like a persistence for thousands of years in history.
And I think this is really interesting kind of from an economics perspective as well, because it kind of flips the causal chain from how we normally think about it. So one thing I remember hearing about is this like Lipset hypothesis, where the idea is that economics kind of causes the culture. But what you're kind of proposing here, and what none proposes as well, that it might be the other way around, that things that happened long ago in the past change the culture, which still persists to today, and that can actually change the economics today, and the technologies today, and the society, and everything we're kind of living in. So this clearly seems to be a very important thing to kind of care about.
Yes, indeed. And like, I want to clarify that this is like a thing I am personally like very confused about. Like, for example, one of the papers that Noon is looking at has to do with like studying the effects of like a slave trade on like modern GDP per capita. And like he finds that a higher slave trade is associated with like lower GDP per capita, and which is of itself surprising. But like we need to figure out like what is the mechanism here, and like one mechanism is like culture, right? It's like a slave trade caused trust to be lower, which also caused like economics to go worse, right? Like the economy to go worse. Another explanation might be like, look, a slave trade was like a huge event. Like by some accounts, the population of Africa was like effectively halved by a slave trade. So maybe this is like a purely economically driven effect. Maybe the setting back the population of Africa by 25 years by my calculations had severe economic consequences.
So presumably here, like understanding the exact causal mechanism is really important. So if I understand you right, if we just look very simply at how much a country was affected by the slave trade hundreds of years ago and their GDP today, we can clearly see there is some relation. But there's kind of a black box in the middle where we don't know exactly what causes it. And this is where we need these natural experiments and these like clear identifications of causality to really help unpack this.
So actually, I think that you've nailed on a problem. I think that for this particular problem, natural experiments are not the solution. Like natural experiments are the tool that we're using in order to determine causality, right? But like from just the causality, like we do not get insight into what are the mediators, what are the mechanisms, right? Um, and here is like one thing that I'm realizing is like the papers of persistence that shine brighter, the ones that I feel more persuaded by and that stand better, like the statistical scrutiny that I subject them to, are the ones where like they try to study these mediating effects through by studying children of immigrants. I think that's like a wonderful idea. Like right now, I'm like studying this paper on like the effects of the Western charts on Western psychology, right? Like Western psychology is like extremely idiosyncratic. People in the West are like very individualistic. They are like very analytical. They have like all these weird like psychological attributes. And the hypothesis that Schund and others are putting forward is the idea that this was caused by the church, the Western church in particular, like trying to the Western church dismantling institutions which like promoted, which were like kin intensive, like things like cousin marriage, for example. And like by dismantling these kind of institutions that force people to be like less collective and more analytical, and that had like a persistent cultural effect, right? And like how do we tell that this is actually like a cultural effect instead of like just affecting the institutions, right? And like the analysis in that paper that speaks louder to this effect is that they study children of immigrants in Europe, which come from different countries, and like by they try to relate like the Western church exposure in these countries to the current attitudes of these children of immigrants, and like be aware that these children of immigrants are like all living in Europe. They are living in like very similar circumstances. So like the only thing that really differs from each of them is their lineage. So this way, like we are able to study the particular mediator, the mediators that are internal and not external, the ones that are transmitted through parentage, rather than the ones that have to do with like modification of the institutions around us.
Could you also maybe just briefly explain this paper about the relationship between agriculture and gender norms?
Yes, so like the main hypothesis here is that cultures that historically use like the plow instead of the hoe, they needed like stronger people to carry them, right? So like men had like a comparative advantage relative to women to use the plow, which led to societies that were like polarized on the on gender roles, right? Like men went out and like did all the farming, while like women stayed in home and like did other tasks. And like the hypothesis is that this kind of like division of roles had like a stick effect. So it led to countries, people whose ancestors used the plow are like more likely to have like views on like gender roles that are more, which are more like conservative in the sense of like, oh, the woman stays at home, the man goes to work.
Yeah, that's crazy to me. Like the fact that the farming tools people used a long time ago can tell us anything about gender norms today in countries where none of those tools are used anymore. That's just really surprising, right?
It is. It is really surprising. My whole relationship with this literature has been from going like, there is absolutely no way that this is true, to going like, okay, but they are treating it like far more rigorously than I expected. There might be something here. And I'm like actually going through like the formal exercise of like checking like what are the possible problems. And like it might be interesting to talk here about like what is like the biggest issue with like these papers, right? What's like the biggest possible flaw that I'm studying. And it's like the issue of like a spatial autocorrelation. Like things in geography cluster together. That's like the iron law of geography, right? And that generates like a spurious pattern. Like if you take like things like altitudes in some random towns in China, and then like you take the map of those towns and you superimpose it over America, for example, it's like very likely that the points where you measure the altitude at the superimposed points in Africa, and you do a regression analysis based on like the original altitude, it's going to show a correlation, which is like absolutely crazy. You're just like fitting noise here. So what is going on here? Well, the fact that like things in geography cluster together, that generates like a certain pattern that correlates things even if they are not correlated. And like it's very important for like this kind of like geographical studies to be mindful of that.
Okay, so we've mentioned a couple of examples of cultural persistence, and something they have in common is that these long term effects weren't foreseen, right? And they weren't intended.
Yes.
But you're interested in all this research, presumably because of its potential relevance to decisions we can make right now, which could somewhat reliably influence the long run future, right? So it's one thing to look back and see that cultural norms have been changed in all these ways, and another thing to figure out what that tells us about how to do it ourselves. So, where our decisions have long lasting cultural impact, how do we make sure that impact is going to be positive? Have you got some impression of how to do that yet?
Not yet. It's something I've thought like a bit about. I do see it as the next logical step, right? I think right now like the research that I'm doing is like the precondition from that. Like before we can even like start considering seriously the possibility of like influencing culture in the long term, we need to figure out if like actually culture is sticky at all, or if this is just like a fool's errands. But I think that you are like exactly on point here. Like the next natural step, should we conclude that like culture is sticky, is to figure out like, well, how do we make it stick to the things that are positive? And like this is a thing that we should be like extremely careful about, because getting locked in on like on like bad values could mean like, could be like an astronomical waste down the line.
Okay, Now, we've been talking about these historical examples, but you've also been trying to forecast a bunch of future technologies and outcomes. So yeah, first of all, what do those two parts of your research have in common?
Yeah, so it might be interesting to look here into how do I think about my research, right? Before we go into that, right? So uh, I'm studying how to predict the impact of like all these different like big things that I cluster under the name of like impact factors, right? Like cultural interventions, new technologies, etc., whatever. And there's like a question of like how do you become good at like predicting the impact of those things? And like the first one is practice, and that has to do with like the aspect of my research, which has to do with like doing detailed case studies of like new technologies. Like I look at like forecasting the effects of quantum computing. I've been looking at forecasting applications of AI to climate change. Like I think those kind of exercises are like both the end goal and like the best way of like getting better at it. But there's like a thing missing, which is that I am forecasting things that I am not going to learn whether they're true or false in a span of like 10 years, 20 years, 100 years. So there's like a missing feedback loop. Like the proven way to become an expert on something is like have like a strong feedback loop, have like a strong ground truth that you can compare your predictions against. And how do we fill that gap? Well, the first one is like the what we need to do is like we need to look at the past. We need to look at like past instances where like where like we have like these examples that we can do like retroactive forecasting on, so that we can like try to use things that have already happened as like exercises for training. But there's like another aspect of this, which is that forecasting is like a relatively tricky, finicky thing, right? Like it's not as simple as like forecasting a thing and you're like either right or wrong. It's like multiple things could happen. You should entertain like multiple possibilities, and it's like a bit unclear about like how do you go about that, especially in the context of like counterfactual thinking, right? If you are thinking about history, like what could have happened in Nigeria if like a slave trade had been different, like that's like a thought exercise, which is like really important in order to build your intuitions, but which like you do not have access to a historical truth about it. So it's important to not only look at the past, but also like have like a very strong formal theory that helps you build this ground truth of like counterfactual reasoning. So like those are like the three pillars of my research. Uh, Doing like detailed case studies, doing like historical research of impact factors, and like understanding the general principles and mathematical foundations behind like forecasting and how this forecast can fit into decision making.
Yeah, so if I'm understanding you right, it sounds like the ability to make accurate forecasts is obviously hugely valuable for any number of reasons. But as a skill, it's really tricky to cultivate, which might explain why good forecasting is less ubiquitous than you might expect. And for the most part, it sounds like that's because there are no quick feedback loops. For instance, it's easier to improve at like chess because you can learn from your mistakes relatively quickly and keep iterating with each new game. But if you've made a prediction about how some aspect of the world will be in 50 years' time, you've got to wait around for 50 years before you can find out if you made a mistake and learn from that. So the big challenge becomes finding a way of getting better at forecasting, like before you retire.
So if I understood you right, like one problem that you have with forecasting the impacts of these things is because they are so long term, and as Finn explained as well. But I'm thinking right back to what you said at the beginning as well, is we've got this kind of counterfactual problem as well, where obviously forecasts don't just happen independently, right? Like they can actually change the events themselves as well, which adds this whole another layer of complexity. So for example, let's say we're going down this road where AI is going to have a really negative effect and it's going to spin out of control. But then all of these forecasts warn us about this. So then we take actions to prevent that from happening, which then means their forecasts are wrong, right? So it's not really the sense that forecasts are just this thing that happen independently, but they actually interact with the world and with our response, and hence with the outcome, which can change the forecasts themselves.
Yes, I think I think that is an issue right now. My kind of like how I'm thinking about it is like I simplify it away, right? I want to restrict my scope to like the case where like I'm not thinking of like these reflective problems, and rather like trying to figure out like, oh, let's pretend for a moment that I'm like I am not part of the world. I'm looking at it from the outside. From the outside, am I going to be able to tell like what's going to happen in the future and what are going to be the effects of like different technologies independent of my forecast? I think this is like a problem that like as we get better at forecasting, it's going to become like more apparent. Like this kind of like reflectivity issue is going to have like real consequences of the world. To an Right now, I don't believe it's that much of a problem because of two sad reasons. The first one is like we are not very good at forecasting. The second one is like people don't take forecasting seriously.
I mean, you might look at climate change, right? Which is a topic scientists have been forecasting the disasters for ages, and yet relatively little has been done about it.
Exactly. Which is like this. It's like this sad situation. If we were in a world in which like we took seriously like the forecast about like climate change, and then like and we acted upon it, then yeah, that will invalidate our forecast. Like the crisis will be averted.
I think it might actually be useful just to think now about what forecasting actually involves. Like, is it just figuring out whether a thing will happen or not and making definite predictions in that way? And if not, where does uncertainty fit into the picture?
Right. So the way that I think about forecasting is like it's obvious that the world is not black and white, right? Like you are never going to have like absolute certainty about like a particular event, and we actually like with training we can become like decently good at like acknowledging like our own uncertainty and like being like better calibrated so that we can tell like look like it this it may be the case that this is going to happen, or it might be the case that that is going to happen. Like I don't know if we're thinking in terms of like trying to predict like when are we going to have a vaccine for the coronavirus. It's like if you say like 100% chance that we're going to have it in 3 months, then it's like sorry, like forecasting doesn't work like that, right? Like you have like a certain information and you're trying to make like calibrated prediction of like what's going to happen, and for that like you need to like spread your probability mass over different outcomes. You have to entertain like different possibilities, different things. That's how it's going to be always. Like you're never going to have like perfect information. What tools do we have in order to like deal with that uncertainty? Like the first and foremost tool that we have is like our intuition. Like we are actually like uh, I think that humans are like decently like well calibrated to like intuitively understand like that perfect certainty is not possible. Uh, this is not something that we usually spend a lot of time like thinking about, but like people can become like reasonably good at like anticipating like possible mistakes, anticipating like points where like plans might go wrong in like unexpected ways. Uh, a second tool that I'm really excited about is like statistical thinking and like quantified forecasting, right? Quantified forecasting is like the practice of like putting like explicit probabilities over like different outcomes, right? And this has like many advantages. The first one is like it lets you use like the statistical machinery that we have been developing over the last 100 years to like the problems that you're interested in, which is like a huge boon. Like that lets you that exposes flaws in your reasoning that you will not have noticed otherwise. And the second one is like it's a tool for collaboration, right? Like when people say maybe this will happen or like it's likely that this will happen, well, maybe and likely are like very vague terms. Maybe when you say it is likely that we will have that Trump will be reelected on the upcoming elections, then for you likely is like 20% probability. Like everybody thinks it's impossible, but I believe it's much has like a much higher probability than other people think. Well, for me, likely is like, oh, I'm understanding like 60%, right? The exercise of putting numbers to our forecasts allows for more precise communication with one another. And I think that's like a great strength to be acknowledged of like quantified forecasting, and what I believe is like the way to go going forward.
I was going to say that's a really good point, that if you're like a political pundit, for instance, or even a politician, and you say things like, oh, there's a serious chance that this bad thing might happen, and then it doesn't happen, well, you can get away with retrospectively saying, oh, by serious chance, I just meant a fairly small chance of a serious thing happening, something like that. If you put probabilities on things, then it's a lot harder to escape the fact that you're consistently wrong when you are consistently wrong. And that can be a really useful thing, right? Because suddenly you're sorting now the people who are just making the right noises and getting away with it, and people who are making genuinely accurate forecasts, right?
Yes, exactly. And that's going to be like a really important piece of the puzzle, right? Because like we're not only interested in like forecasting, but we're interested in our forecasting. Like we're not only interested in our forecast being precise and accurate, but we also want our forecasts to be used for decision making. And in order for that to happen, like you need to solve like the attribution problem, right? Like you need to sort out good forecasts from bad forecasts.
This makes me think of this Nate Silver quote, which is that when communicating with politicians or like the general public, you should always forecast an event as having like a 40% probability, because that's large enough that people will be scared by it, but still low enough that if it doesn't turn out, like you don't harm your credibility.
Exactly. That sounds like great advice.
You mentioned the word calibration a couple of times. Can you just explain what it means to be well calibrated?
Okay. So like when people think about forecasting, I think they put a lot of emphasis on precision. They want their forecast to be as true as possible, as close to truth as possible. But that generally leads to like people making like very overconfident statements. And for me, it's like far more important to be well calibrated. It's very important that the forecast that you make correctly reflect the uncertainty that you have around the topic. Like out of 10 times that you predict something happening with a 70% chance, it happens like 7 out of 10 times. Why do I believe that this is so important? Like the most important reason for me is that it allows me to trust experts. It allows me to take a prediction that an expert is taking and like understand exactly how much uncertainty he has around it, and it allows me to combine it with like the predictions of other experts in order to like reduce that uncertainty. Like if I have like lots of precisions, lots of forecasts which are like vague in the sense of like they are like very uncertain, but they are like well calibrated, then they are going to aggregate well together. Like if I have a bunch of like calibrated forecasts, I can combine them and get a better forecast. If I have like a bunch of like overconfident predictions, then there's like not a very sensible way of like aggregating them in order to getting closer to truth.
Okay, this is a slippery question, but I'm wondering, so when you say something like, I assign an 80% chance that such and such a thing will happen, what's actually going on there, right? So do you mean if you rewind and run the world 100 times, this thing will happen 80 times? Or are you saying something more like, given what I know, there's a good chance this thing is basically bound or guaranteed to happen, but I might have missed something or made a mistake? In other words, is there a real difference to be drawn here between risk and uncertainty? Like, doesn't just assigning one number, one probability, muddle these things up?
Different people here have like different views about like how we should trade probabilities. In my personal view, the correct way of like treating like forecasting probabilities is as an inherently subjective thing. Like when I'm telling you that there's like a 40% chance, like there's like a lot of assumptions that I'm loading into that. there's no such thing as like an objective probability of something happening. It's like probability that I assign to something happening, given like the context of the situation, given the assumptions that I'm fitting into my model, given how I am thinking about the world. So when people are like telling me like, oh, how do you distinguish between like objective probabilities and like probabilities that are not so objective? It's like, for me there is not such a hard distinction. I think that a very particular pitfall that we need to avoid in terms of like forecasting is like having people take it too seriously. Like for me, forecasting is like a tool to acknowledge and express the uncertainty we already have. Uh, it's not so much a way of like assertively stating something objective about the world, which also in a sense it is, but it's more like trying to have like more a more nuanced takes to like truth and falsehood.
Yeah, that makes sense. Now, people have been trying to forecast important events for a very long time, and maybe a bit more recently, they've been doing it in a more quantifiable or measurable way. Turns out some people are better forecasters than others, right? I'm curious to know what kind of attributes or skills do good forecasters have as compared to mediocre forecasters?
Okay, so here there's like this pioneering body of work that you'll be familiar with, which is the work of like Philip Tetlock, who has been looking at judgmental forecasting and like what makes people very good forecasters. And right now, this is like in a stage of, it is a bit of a cargo cult in the sense of like we have identified like the attributes of like people who are like good forecasters, but we are not like super sure of like which of these attributes are like actually important. And right now this is like an ongoing field of research of like trying to identify like what are the good things. One of the most impressive results that they got is like from their learnings about the attributes of the most impressive forecasters they identified, is they designed like this 1 hour program, which is it's like a very short reading. It's called like the 10 Commandments of Forecasting. And like they show that by having people read that in a randomized control, like they designed a randomized control triad where they showed that by having people read that, they improved measurably their forecasting skills.
Yeah, that is very surprising. What kind of stuff do they teach in that program?
So like the kind of things that are being taught in that program, the one that I feel is more important has to do with like reference classes, right? It's like trying to situate an event that you're trying to forecast in a larger class of like events that you have observed in the past, right? So like if you're trying to forecast like what are the chances of a particular cryptographic code being broken in a given year, then you may look at like past standards for cryptographic security and like look at like how long it took until each of these standards was like successfully attacked. And that's going to be your reference class, and you can come up with like a simplified statistical model with like from this information will give you like the annual chance of a particular of this particular code that you're studying being successfully attacked on a given year. That's not enough. Like after you do like that reference class forecasting, then that's the point where like you should take into account like the specifics of this case. Like maybe people are clamoring that this cryptographic code is like really really good, or maybe there is like a researcher who has like published a preprint which hasn't been reviewed yet, claiming to have successfully attacked the code, right? So that's the point where like you take like this base probability that comes from a reference class and you update it. And people, when it comes to updating these reference class probabilities, like people do it in an intuitive way, and they seem to get better at it with practice. It's not something that we understand like very well now, but humans seem surprisingly competent with practice, are like getting better at this.
Are there cases where there just is no reference class because the thing you're interested in has no precedence? Like, if you want to know the chance this century of some humanity-ending catastrophe. Well, none of them have happened before, so it's tricky to know where to start, right? Is that a worry?
That is definitely a worry. I will argue that a field of work that I'm particularly excited to start seeing examples of, and I think that we will start seeing examples over the next 10 years, is like trying to figure out like good reference classes for these kinds of events. So like, for example, in CISR, one of my colleagues is like looking at like historical civilizations that collapsed and using that as like a reference class to study the chances that our civilization is going to collapse.
Okay, got it. Now, let's talk about why efforts to improve forecasting ability are apparently so hard to come by.
I think this fits directly into the reasoning behind my research program. It has to do with the lack of effective feedback loops. When people are like engaging in forecasting, like traditionally you say like, okay, 40% chance of everything happening, as like we were jokingly referring to before. And then it's like, well, it has happened or it has not. But in either case, were you wrong? Were you right? Should the probability have been higher? Should it have been lower? Are there gonna be like any consequences for you by getting this probability wrong? And like I see us as a society, like we're starting to build those feedback loops. I'm like really, really excited about like this new program by the Center for the Study of Emerging Technologies of the U.S. government, where like they are explicitly, an explicit call for forecasters to join and try to make like quantified forecasts about security issues.
Now, maybe there aren't so many obvious incentives for non-profits and governments to get good at forecasting, right? But aren't there pretty strong profit incentives for companies, at least, companies of a certain size, to do that? In which case, why does it look like very few for-profit companies seem to care about this at all? Or am I missing something?
There's like an important puzzle here to be solved, which is like, why do companies and why do humans don't use forecasting by default? And one possible solution to this problem has to do with like maybe the kind of things that we're interested in are things that are inherently hard to forecast. One, and like two, it doesn't matter that much to forecast them exactly, as long as you get like the overall direction of the trend, right? So like this is like the idea of like heavy tail distributions, right? This is like the idea of like if you're trying to make like a society perdure, the things that you should be worried about are like the most extreme outcomes, because those are the ones that threaten to end your civilization permanently. So in those situations, it becomes like slightly less valuable, like trying to forecast like what's the exact probability of like a particular bad outcome happening. Like you only need to know that it is plausible and a way of like dealing with it. So your resources are better spent on like preparing for like for this averting this bad outcome.
I mean, one thing that I'm thinking of as well, and I've got no clue really how this relates to all of this, but it's like the idea as well of, I mean, kind of like peer pressure or like group thinking, and then also like risk aversion preferences. Like I'm thinking, especially in the context of like for-profit companies, that there is like a big incentive to not deviate too much from your competitors, especially if you're very big and the stakes are very high. Just because there is almost sometimes like just safety in numbers. So it's almost better to, or there it certainly is an incentive just to stay with the status quo.
Yeah, definitely. Like we need to make like a concession at some point, in the sense of like what you're saying, like sort of like implies that the market is not being efficient, right? Because there's like people who are like leaving money off the table by not experimenting more, by not trying out the things.
Yeah.
And like maybe they're acting rationally, in the sense like the question is like whether they're acting rationally or not, right? And like if they are acting rationally, we're left to explain of like why aren't they using forecasting? And if they are not acting rationally, then we are like left to explain like why is that happening? Why doesn't nobody have thought about this before?
Yeah, I guess there's some kind of explanation in if a company is considering introducing some system where individuals get feedback on their forecasts, and they're also forced to put numbers on the claims and predictions they make, it's pretty likely that some fat cats, some senior executives are going to be called out as mediocre forecasters who have fudged their way to the top. And that risk is maybe enough just to pull the brakes on ever introducing it in the first place, right? Because these are the people making the decisions. That's just speculative. I don't know.
That may be the case. In that case, I guess this fits into a narrative of forecasting only being useful when you already have the basics down. So you already need to be a certain size in order for forecasting to be useful. Otherwise, you should just be thinking of other things. If you're a startup, you should not be trying to exactly maximize your profit. You just need to stay alive. You just need to live to see another day, right? So at that stage, it does not make sense for you to build an infrastructure of forecasting. And by the point it comes where it starts to make sense to invest in this forecasting structure, then you no longer have an incentive to do so because the people making decisions feel threatened. That's another explanation. But here again, I'm really confused about this whole topic. Another thing might be that forecasting is a public good. Good forecasting requires extensive collaboration. We need a Wikipedia of forecasting where people aggregate forecasts because the world is complex, and in order to figure out whether your profits are going to be up or are going to go up or down, you need to take into account a lot of things about the world. And building that kind of infrastructure that aggregates forecasts about the whole world, that's a huge coordination problem. No single company is going to have the resources to build it, and doesn't want to be the sucker to build it, right? Like
And you've got other smaller things as well, right? With the which are explicitly forecasting markets, like Metaculus, or the super forecasting kind of competitions and stuff. And there was a time as well where the US, famously tried to introduce this betting market on terrorism and all these crazy outcomes as well. Cool. So I think we've talked a lot about kind of forecasting and the whole decision making process that kind of goes into it, and the risks and the like of it. I was wondering if we could maybe very briefly talk as well about one of the applications of your work in relating to forecasting. So you can almost kind of choose, I guess, between quantum computing or climate change, both of which you worked on.
let's talk about quantum computing, for example.
Cool. Let's talk about quantum computing then. Can you first explain, I know this is a very difficult topic, but can you maybe give us a non-technical explanation of what quantum computing is, and perhaps more importantly, what quantum computing isn't?
So the short and frustrating answer is no, I cannot. People who are smarter than me have tried and failed to give intuitive accounts of quantum computing. The slightly longer, slightly less frustrating answer is I think that for this question, it's better to think in terms of what quantum computing can do in terms of when compared to classical computer, rather than what it is. And for the details of what it is, I would like to recommend the listeners to go check out Quantum Country, the website by Michael Nielsen and Andy Matsusak, where they are doing it's a very interesting academic experiment where they're trying to integrate space repetition on teaching quantum computing, and they do an excellent job at it. In terms of what quantum computing can do, one of the most surprising results and one of the most widely useful results in quantum computing is the fact that you get a quadratic speed up on pretty much everything. And let me explain this. Classically, if you have a problem and it has 100 possible solutions, then what you're going to be forced to do is you're going to have to try each of the solutions until you find the one that works. And roughly, you're in the worst case, you're going to have to do 100 operations, right? You're going to have to do in the order of checking each of the solutions individually. With quantum computing, you can do this very clever trick, which is called the Grover algorithm, that allows you to perform this search far more efficiently. In particular, it will take quadratically less steps. So like for 100 possible solutions, like you will take in the order of like 10 steps in order to figure out like which is the solution that works. And this is super applicable. This is like super general for pretty much any problem in which like once you find a solution, you can easily check that the solution is correct. You're going to be able to apply like the Grover algorithm. And this is like pretty interesting, but there's like a question of like, is this practical? And sort of, maybe, we don't really know. Like there's some historical examples of like quadratic speed ups having been like important for computer science. Like the more salient one is with the Fourier transform, which is like an algorithm using in digital signal processing. There was like a quadratic improvement that was like, it had like a long history, but its final form was like developed around like around the 70s, if I'm correct. Like this allowed like the whole field of like digital signal processing to flourish. It was like really, really important. And there's like a question of like, with this quadratic improvement that's gonna come from like quantum computing, are we gonna see a similar thing? And like, for the most part, I'm like quite pessimistic about this. Quantum computing requires like a specialist hardware. It parallelizes like really, really badly. It's like really, you cannot really like split a task in four, send each of them to a quantum computer, and like get the same quadratic speed up. So yeah, so I'm like moderately skeptical. Now, there's like a second thing that quantum computers can do. And it's like there's some problems, some very particular problems with like a very specific structure where like you do not get a merely quadratic speed up, but you get like an exponential speed up. And that is huge. That's literally the difference between like being able to factor a number in a matter of days versus factoring a number in a matter of until the universe ends. And right now, like a very important research question in quantum computing is like, what are these problems in which like we can get an exponential speed up?
Before we talk about those problems, I think it might be useful just to explain what we mean by quadratic and exponential speedups.
Yeah, so like the basic way of thinking about this is like with a quadratic speed up, if something would have taken like 100 steps, then with a quadratic speed up, it's gonna take like the square root of that, right? So it's gonna take like 10 steps, which is a huge. It's like pretty good, but it's nowhere compared to like an exponential speed up. An exponential speed up means that's gonna take like logarithm of those steps. Like right now, I'm using lots a very loaded terminology, but the way that I want people to think about this topic is like a quadratic speed up is like the difference between like doing a thing in a matter of days versus in a matter of weeks. Whereas like an exponential speed up is the difference between doing something in a matter of days or doing this in a matter of like 100 of millennia.
Yeah. So in this second kind of problem where you're getting this exponential speed up, you might think of it like it takes a classical computer some number to the n steps where the problem scales with n. You give it to a quantum computer and it can do it in roughly n steps. Now, when n is big enough, that difference isn't just a difference of, 10 or 100 fold. Like you said, it's like an astronomical difference. So these problems, where we can find them, are like enormously important.
Exactly. That's exactly the thing.
So can we talk a bit about how forecasting relates to this and maybe how our discussion before is relevant for quantum computing? I guess on the one hand, there's the conversation about how likely progress in quantum computing is. And on the other hand, there's forecasting what impact quantum computing might have on the world.
Yes, which are exactly like the two halves of my research. There's like one very quantitative work that I'm doing with like Jess Riedel that has to do with like forecasting. When are we going to have like quantum computers of like different capabilities, which is like really groundbreaking work. Like we're like working with like really few data. There's like very few past examples of like people trying to forecast this in a quantitative way. The second aspect has to do with like it's more qualitative. It has to do more with like talking to experts and like understanding like what are going to be the exact capabilities of like quantum computing and what are the practical applications. And it requires like what I will say like a lot of like moderation. Like it's very easy to get driven by the hype, right? Like you invest a lot of time on a topic on quantum computing, and then it's like quantum computing is like the coolest thing ever. It's going to solve everything, and it's like, wait, hold your horses. Like we need to understand exactly like what are the problems that it solves, and like whether those problems are like bottlenecks in the respective areas, or whether it's like a lower hanging fruit somewhere else in those areas. And that's exactly like the exercise I did for like the three main applications of like quantum computing.
Well, let's talk about those applications. What are these problems where you get really promising exponential speed ups, which quantum computing would be most useful for?
Yes, exactly. So the first most important one, also the one that is more widely known, is that quantum computing allows you to factor numbers really fast. And like this may seem like innocuous enough until you realize that modern online security relies on the fact that you cannot factor numbers fast. And this is like a huge problem in the sense of like this is going to force us out of our current cryptographical standards. We're going to need to switch how we think about like online security due to the fact that quantum computers are possible and they are able to successfully attack our current cryptographical standards. I spent some time talking to the head of research on quantum cryptography of the National Institute of Standards and Technology of the United States, and I got out of that conversation reassured that like we have like credible candidates for like quantum resistant cryptography that could be implemented on like modern hardware. Well, the hardware will need to be adapted in order to efficiently perform like these computations, but it's something that is like within our reach to implement. And they are actually running right now like a multi-year contest where like they are pitting like different proposals against one another. Where the goal is that in a matter of like less than 5 years, they will select a standard to recommend to hardware providers as they want to implement.
So let me see if I can get clear on that because it sounds kind of weird, right? So, you learn in maths that you can factor a number into its prime factors, right? And there's an interesting property of doing this prime factorization, which is, turns out it's really hard to do it. It gets slower and slower as the number gets bigger. But it's always pretty easy to multiply those prime numbers and get the big number. So there's a kind of asymmetry there. Now, it turns out that that's useful in cryptography. So when I buy something with my credit card online, it's relying on the fact that it's hard to crack that big number into its smaller prime numbers. You're saying, and this is kind of worrying, that quantum computing promises a way of doing that much more efficiently. In fact, a way of doing it so quickly that we might break those ways of doing cryptography. And so what I'm hearing is that we might need to pretty quickly change our cryptography standards, right? Otherwise, things are going to become very insecure very quickly. Is that right?
That is correct. I guess that I want to add some nuance at like what do we mean by quickly, right? Like right now we do not have quantum computers that can factor numbers greater than 45. So right now we do not have the capability to perform these attacks, and there's like a forecasting question of like when are we going to have those capabilities, which is exactly what me and Jess Riddle have been engaging with for like the past few months. And like again, like our work is like very it's not proven work, right? Like we're trying something that hasn't been tried before, so I don't feel comfortable like giving our predictions as like matters of fact, right? This is more of an exercise of like can we actually get some predictions, and like maybe 20 years down the line we will find out like how well calibrated our predictions are. But I can talk about like expert opinion, and like expert opinion is that lots of experts put like that by 2035 we might have this capability with like 50% probability, which is like it's like a decade from now, uh, it's in principle enough time to make the switch to like quantum resistant cryptography, given that we already know quantum resistant cryptography. Like we're going through like the formal process of like uh, verifying it, trying to attack it, trying to find holes on the proposals that we already have. But like we already know that we strongly suspect that it is possible in principle and that the solutions that we have identified work. But it's a matter of like implementing them, right? The process of like testing them cannot really be rushed. In fact, like we really need those things to be secure. Like if we were to change like modern cryptography with like a completely untested new cryptography, like that will be a net bad for like security.
We've already switched cryptography standards in the past, right? A couple of times. So it's promising that it's at least feasible.
Yes, exactly. And I think that the past times where we have made those switches provide like a very good reference class in order for us to understand like how quickly those changes can be made. And like right now, given my forecasts about like when we're gonna have like quantum computing of different scales, like given my forecast about how fast can we get like quantum cryptography, quantum resistant cryptography, I'm not very concerned about this problem. I think that NIST is doing like really excellent work in this area. I think there's like lots of people who have this problem under control, and we're gonna be able to, as a society, handle the transition.
Okay, that's encouraging. So we've talked about this one application of quantum computing to cryptography in communications and in buying things online. What about any other applications?
So there are like two other more speculative applications where like we might see an exponential speed up, which are artificial intelligence and like simulation of physical systems. Um, in artificial intelligence, there has been like lots of talk lately about like quantum machine learning, about like a specific machine learning applications that could be sped up using quantum computing. My impression is that those applications are generally like overhyped. In order for us to get like exponential speed up on things like faster recommender systems, then we're gonna the problem to be solved needs to meet like very particular requirements. So like it needs to be sparse in a specific way. It needs to be a problem that doesn't have lots of parameters. And most importantly, it will require like a fast way of loading the problem into a quantum state. And like right now, with our current understanding, when you try to load this kind of problem into a quantum state, in the process of like loading it, you waste so much time that you essentially like do no longer get like a speed up. Uh, Now there's like some proposals for like what's called like a quantum RAM, quantum memory, computer memory that may solve like or assuage this problem. But right now this is on a very like theoretical stage, and like my take on also not only this, but like there have been like very egregious examples of like people finding like an exponential speed up on machine learning applications or like algorithms in general, and then like 1 year later somebody comes up of doing it as fast on a classical computer, right? So like not all apparent speed ups that we know of today are like actual speed ups. Maybe it's just a case of like we actually haven't figured out how to do it fast on a classical computer. So for artificial intelligence, my take is like it may have an impact in the future, but I could be betting on like no or like a very small complementary role. The other big application is simulations for physical systems, and this is like a topic that I am less of an expert on, so take everything here with a grain of salt. But the big idea here is that natural systems are quantical in nature, right? And in particular, like it was already Feynman who was saying that well, one of the big applications of like quantum computing is going to be that we're going to be able to like if we want to efficiently simulate like natural systems, we're going to need to make computations on a similar way to how nature does its computations, right? To how nature figures out that like atoms should rotate like this way or that way. And it is true. We can solve like quantum equations, physical quantum equations faster in a quantum computer. But there's still like a big issue here, which has to do with like you need to write those equations. And like as physicists may tell you, as long as you try to write the Schrodinger equation for more than one particle, things get like very unruly, like very fast. And that means that the bottleneck is not like the bottleneck right now on like doing like in silico simulations of nature doesn't have to do so much with like solving equations faster, which is what quantum computing is good for, but rather like actually modeling reality and like writing down the equations that describe reality. So as you get bigger and bigger, like this becomes like it becomes like increasingly less plausible of like whether this is going to have like applications. So like for example, people talk a lot about like, well, if we can simulate the effect of like medicines, this is going to help a lot for like drug discovery. And it's like, well, not really, because like the bottleneck right now in drug discovery is in like figuring out like how different particles are going to interact with the body. And you're not going to be able to write down like all the complicated stuff that goes on in the body into like an equation that you're going to be able to feed into a quantum computer, at least in the short term.
I'm getting the impression that what the application of quantum computing to AI and to simulating physical systems have in common is that they may well deliver this speed up some way down the line where we overcome the kind of obvious problems. But the bottlenecks in both cases don't have much to do with the kind of problems that quantum computing promises to solve.
Exactly.
So that was a very sobering and I'd say nuanced talk as well about quantum computing and what it can do and what it probably can't do. And it's definitely changed my mind, I think, about how I think about it, which brings me on to ask the question we ask all our guests, which is, what significant thing have you recently changed your mind about?
Oof. Yeah. I think that one significant thing that I have changed my mind about has to do with like historical persistence. I was when I walked into this area, I thought that I was going to find like very sketchy p-values, like people finagling statistics in order to get the results that they want. Instead, what I found was like a very rigorous field where like people have like a very nuanced take on like how to identify like causal effects through history.
And now, what is your impression of it now?
My posture in it now is like they actually know what they're talking about. They're actually doing like good statistics, rigorous studies. There are some subtle questions that are being debated on the field that have to do with like spatial autocorrelation and like the validity of the results, which like makes me hopeful that this is like a, a, a way of like doing social science that is going to become like more rigorous and like more popular in the future.
Yeah, that's actually quite an uplifting thing to think about. So the very last question we have, which we ask all our guests, is what 3 books or articles or other pieces of media would you recommend for anyone interested in finding out more about what we've talked about? And we've talked about a fair bit, actually, this episode. We've covered a lot of ground.
So we have talked about forecasting. I'm going to be boring. I'm going to say go read Super Forecasting by Ted Block. It's a great book. It will make you a better forecaster. Go check it out. We have talked about historical persistence. And for historical persistence, I do recommend a lot the work of Nun. If you're like a budding economist, I do really recommend that you Google his papers. He's like very accessible, very readable, and like you will learn a lot from the experience. This may be off-putting to some people to be asked to read the paper, but like really it is worth it. And we have talked about like predicting the future. We have been talking about like the impacts of the future. So I want to recommend The Precipice by Toby Ord, which is a recent book where he talks about like existential risks. Like he has the courage of like putting probabilities to like the different existential risks that we are dealing with in the present. So definitely go check that out. And like I encourage other authors to be as brave as like Toby Ord and like put the probabilities on the books.
Jaime Sevilla, thank you very much.
Thanks to you too. Have a great day.
That was Jaime Sevilla Molina on forecasting, cultural persistence, and quantum computing. As always, if you want to learn more, you can read the write-up at hearthisidea.com/episodes/Jaime. That's Jaime. There you'll find links to all the papers and books referenced in the episode. As always, we would be really grateful if you could leave an honest review on Apple Podcasts or wherever you're listening to this. It's still probably the most effective way of getting more people to find out about the show. If you have constructive feedback, there's a link on the website to an anonymous feedback form, or you can just drop us an email. That's feedback@hearthisidea.com. We'd love to hear from you. And of course, if you would like to support the show more directly, you can also leave a tip by following the link in the show notes. Thanks very much for listening.